deal with nano? Nano at its most fundamental level is just science at a small scale. So what's so big about it?
Well, that's a great question. The big deal with nano is surface area. We're going to show you a couple of experiments today in which surface area plays a crucial role.
In this experiment, we're going to show that lycopodium powder does not react when there's not much surface area, because right now it's all clustered together, and it's kind of like a fire. You can't start one unless there's a lot of space for the air to get through. So it's like the same in this case. So it's all in a clump, and so when we try to light it on fire with this lighter, it's gonna burn a little bit, but not very much. It's not very spectacular. This is because only a limited amount of the powder can react at once, since it needs to have contact with oxygen to burn. Thus, the limited surface area limits the speed of the reaction. But if we atomize it, spread it out so that each particle is surrounded by air, we can see what a reaction at the nanoscale can look like. Alright, for this experiment we're using a wash bottle and tube setup, and there's lycopodium powder in here, and we're going to shoot it out, and like a fine spray, then we're going to light it on fire with this lighter. This might not be good.
Wow, what a reaction. And this isn't some factory synthesized magic compound with super mysterious chemical properties. It's lycopodium powder. It comes from the spores of the lycopodium plant, and though it isn't quite nanoscale, because each spore has a diameter of about 30 micrometers, it's pretty small and shows what increased surface area can do. It's used in pyrotechnics and movies because of all the cool fire possibilities.
But this combustion reaction isn't unique to the lycopodium plant. It can also occur from the dust of other plants, including grain. You ever heard about a granary explosion? What we just showed you was not even an ounce of lycopodium powder. Imagine an inch of dust at the bottom of the silo being stirred up into the air and then add a single spark, and boom, the silo glows. This is an example of nano reaction in real life.
This is a contraption that will simulate what happens when a grain silo gets set on fire. In here, we place our lycopodium powder, which is highly flammable, and we will be lighting a candle down here. Using this, we will give it a squeeze and pump air into the chamber, which will then disperse the lycopodium powder, setting it on fire and blowing the top off because of the increased surface area. Alright, and now I'm going to do the explosion. That's the power of nano.
It may be small, but the surface area gives it a lot of speed in reaction. And that's just one of the ways that properties are affected at the nanoscale.
Nanometer. How big is a nanometer anyway?
This is a picture of a human. Let's try and relate that to a nanometer. This is a strand of her hair. Let's get a bit closer.
This is a scanning electron micrograph of a human hair. This scale bar is 20 micrometers. 1 micrometer is 1/1,000,000th of a meter.
1 micrometer is also 1,000 times bigger than 1 nanometer.
Let's try it again. This is a picture of red blood cells. One red blood cell is about 7,000 nanometers, which is 7 micrometers.
Let's look at one more example. The desert marigold. Here's a close-up of the pollen. The length of the pollen is about 30 micrometers.
A nanoparticle could actually fit through one of the holes in the pollen grains.
Sometimes elements on the nanoscale can have unexpected properties. One of these elements is gold.
Here's bulk gold. This is probably what you're used to seeing.
At the nanoscale, gold changes colors. Here are 2 examples of different concentrations. The one on the left is a lower concentration than the one on the right. Depending on size, gold can even appear green or blue.
You're going to be using samples like these in the lab.
We're here at the characterization facility.
Let's go inside.
This is a transmission electron microscope, which we call a TEM. So that's T for transmission, E for electron, and M for microscope. And you can see this is a really big instrument. This is one of the instruments we use to see nano. How do you see nano when nano is smaller than the wavelength of light? That's the big question, right? So, at the University of Minnesota, we use this very tall instrument, the TEM, the Transmission Electron Microscope, to look at nanoparticles and other extremely small objects. So let's take a look at a sample. So how do we look at nanoparticles in the TEM? The first thing we have to do is get them into the microscope. We put the nanoparticles onto a tiny disc, like this one. This disc is 3 millimeters across. It has a film onto which we put the nanoparticles. And we place it into a sample holder, like this one. Place the sample onto the rod, and then I can close this down. And then the sample is ready to go into the microscope. When I come over and place the sample into the microscope, you can see here I already have a sample in. But you can see where the sample rod goes into the microscope, and then my nanoparticles now are ready to be viewed. So now we're ready to look at our nanoparticles. We have our sample rod here. The electrons are generated up here. They travel down through the column. They go through our sample holder. And then we can actually see our image down here. Right now you're looking at an image of a sample on the fluorescent screen. The electrons strike the fluorescent screen and it glows green, letting us see the image. But it's a lot easier to use the computer. And so we can also look at the image on the computer screen. What you see here are gold nanoparticles, just like the ones we're going to work with together when you guys come to campus. So these are gold nanoparticles that are around 10 to 15 nanometers across. And this is what an image of those particles look like. These dark things, those are the gold nanoparticles. And this background, that's the film they're sitting on. And we can zoom in so we can look at more detail. Let's look at an image by one of the students, Hallie. Here we have 3 gold nanoparticles, and they are all about 20 nanometers across. And we can even zoom in some more. So let's zoom in some more. And we'll go to this image here, which is a single gold nanoparticle. So you can see these dots and lines. Those dots and lines are direct atomic structure image of that gold nanoparticle. So we're actually able to see the atomic structure of that object using the transmission electron microscope.
So why can't we use a normal microscope to view nanoparticles?
That's a great question. Nanoparticles are so small, they're smaller than the wavelength of light.
Okay.
So we can't see nanoparticles using regular light. Electrons have a wavelength that's smaller than nanometers, which means we can see nano-sized objects. In a light microscope, we use glass lenses to focus light. In an electron microscope, how do we focus electrons?
We use electromagnetic lenses located along the column of the instrument.
So what do we learn by using the TEM to characterize nanoparticles?
We learn a lot of things. We can learn about the size of our nanoparticles. So earlier in this video, you learned that properties change with size. So we need to know the size of the particles. We also might need to know the shape of the particles. So if a particle is shaped like a rod or like a ball, they might behave very, very differently. We also might want to know whether they're sticking to each other. Sometimes particles behave differently when they're stuck together versus staying apart. And all those things matter in different applications. For example, using gold nanoparticles to detect cancer, using quantum dot nanoparticles to make solar cells. These are all important things that we need to know to make the best nanotechnology. This is one of our old TEMs, and we cut it open so people could see what it looks like on the inside. So remember, Michelle said that we use electromagnetic lenses to focus the electrons. These are coils of copper wires that allow us to make the electromagnetic fields that allow us to focus the electrons. So then this here, that's the column. The electrons go through the sample, which is here. And then the electrons keep going through more and more and more lenses until you get the image down at the bottom.
Alright, so by now you guys have seen different examples of what nanotechnology can do. We're going to show you guys another one. So basically what we've got here today is hydrogen gas with platinum. Hydrogen gas reacts with oxygen to form H2O, which we've shown you in this reaction. So 2 molecules of hydrogen gas combined with 1 molecule of oxygen. And they just, like I said, 2 particles of water. And what's going to happen is, since this reaction doesn't normally happen that fast, we have added platinum as a catalyst, which we have here on this wire platform. We've got some pellets right here, and we've got the bulk platinum.
Alright, so the bulk platinum has more platinum in it than just little pellets do. But the pellets are infused with nanotechnology, so they actually have a greater surface area, and what matters for the reaction is surface area. So if you look at the bulk platinum, the surface area of the bulk platinum is only about 1.4 centimeters squared. But if you take the pellets, there's 4 pellets on that wire. They each have about 50 centimeters squared of surface area per pellet, and there's 4 of them, so that's 200 square centimeters. So we'll see what that transfers with our reaction.
As always, guys, safety in lab is very important. Goggles on. Alright, so we're going to start out by shooting the hydrogen gas at the bulk, and we should be able to tell if something is happening if we get some heat off of it, because then it's an exothermic reaction.
Alright, I'm opening up the hydrogen right now, and we're going to start shooting at the bulk platinum.
Alright, so I'm currently shooting at the bulk platinum, like you said. And the same reaction we talked about earlier is happening, but it's not happening quite as well as we would like it to. So I'm going to switch it over to the platinum pellets now. You guys should be seeing a little bit of an orange glow on your screen.
That lets us know that the exothermic reaction is happening.
Flame on. Flame on.
There it goes. We got the flame.
Fire. Alright, one way to think about this in like a more day-to-day type of way is with like sugar cubes. Say you want to dissolve a cube of sugar in water and you just throw it in the water. The sugar cube by itself doesn't really dissolve that well. Like you have to stir, you have to mix, you have to do something to make it dissolve better. Now take a cube of sugar versus like a spoonful of ground up sugar. And that sugar, you throw it in there and it dissolves a lot quicker than what a bulk sugar cube would. So that's one way to think about this. Like nanotechnology with the larger surface area is much more effective.
Alright, and so one application of scientists actually using this is they're researching into how to use it on hydrogen-powered cars. Since the platinum increases the reaction, and you saw how we got a flame out of it, they can use this to actually power engines and potentially make cars like the Jetsons. I don't know. Alright, good luck, guys.
So this is ferrofluid. You might be asking what it is. Well, we'll tell you that, why it's shaped the way it is, and what it's used for.
So what is ferrofluid? It's made up of magnetite nanoparticles that are covered in surfactants so they don't clump together. And then all of those particles are in a fluid, either water or some other organic solvent.
Alright, I'm going to tell you guys why ferrofluid is shaped the way it is. And the reason is because it's magnetic, so when you hold a magnet up to it, the particles of ferrofluid are trying to collect at the points where the magnetic field is strongest, so it forms spikes.
So you might be asking yourself, what is ferrofluid used for? Well, it has several different uses in many different fields. For example, in electronic devices, it is used as a liquid seal in spinning hard disks. In medical technology, it can be used as a form of cancer treatment, where it's injected into the body and held in place with a magnet. There, it is vibrated to heat up to kill the cancer cells while causing no damage to the surrounding tissue.
Starring Mitch and Grant. Look how excited they are as they run in to start their work on hydrophobic nanoparticles. They're happier than a fluorine atom getting an extra electron.
We coated part of this plate with a hydrophobic substance, but left the middle square untouched. All the water pools into the middle square as it's repelled from the outsides. It creates sort of a square of pushy, jiggly water. Now, what's causing this is a bunch of nanoscopic cones pushing the water out from the outside. This has been seen in nature, like on lotus leaves, where we've seen microscopic cones push water droplets off, and they ball up and roll off. These cones reduce the contact area of the water on the leaf and force the water to ball up and roll. Now, the material we've coated this plate with was materially synthesized industrially to create nanoscale cones, improving upon the effect originally found in nature. You can see the balls on this plate rolling up and collecting together, none of them really sticking to the plate surface.
Now, as these droplets are moving around, the only reason we use the dye is just so you could see it better and how it's not actually sticking to the plate where we place this nanoparticle material. And now you just get to watch an awesome video. Commence the dubstep. Now, as you can see, the droplets, when they get to that middle square, are attaching to the plate. That's because we did not treat that middle square with this material. Now here's some more video of the water droplets pooling on the plate, and more dubstep.
Okay, here we coated a t-shirt with the same super hydrophobic substance, and as you can see it's cotton, so normally the water would soak into the shirt, but here it is repelled, and then we just kind of play around with that for a while.
Wait for it. More dubstep. And Grant is just so excited for science. Don't you just hate when you get liquid squirted all over you? Well, now it's not a problem with our new nanoparticle material. As you can see, the water just bounces off the shirt just around the square area where we've applied the material. Look at Mitch. Well done, well done.
Hey baby, are you made of copper and beryllium? 'Cause you are cute.
Okay, now we're doing the same thing as before, but this time with chocolate syrup. And as you can see, one of our interns actually bled into our t-shirt. Just kidding, but from the earlier experiment, it soaked through from the other side. It still works, it just is stained red now. But as you can see, it repels the chocolate syrup, just like it did with the water.
Now, as you guys all know, chocolate syrup's pretty sticky. Don't act like you're not impressed. That's pretty cool.
Nano's awesome!
As you can see, nanoparticles have endless possibilities. Think to yourself, what kind of applications could these nanoparticles have? Dubstep!
I'm about to make the ill type moves.
Technologies such as your iPhones and your galaxies have tiny nanoparticles, have titanium dioxide nanoparticles. These bandages have silver nanoparticles in them. So do these awesome looking sunglasses. And these never wet, multi-surface liquid repellent treatment. They also have nanoparticles in them. As is this MacBook Pro laptop from Apple.
So these cadmium selenide nanoparticles
change color depending on their size. All 5 vials, all the same elements, but different sized nanoparticles, in this case also known as quantum dots, starting with this orangish red color, the largest, all the way down to purple, the smallest nanoparticles. When we shine UV light on them, the particles get electronically excited, and when they relax, they emit a certain color of light depending on particle size.
So what are some current applications of nanotechnology?
Anti-reflective coatings like for your glasses. Renewable energy like solar cells.
Energy storage like new batteries. Anti-icing agents for airplanes.
What are some future applications for nanotechnology?
Using nanoparticles in your body to make structures so that your cells can regenerate.
Flexible electronics.
Cure for cancer.
Flexible displays.
Invisibility.